Hello, welcome to another problem session. Today we will talk about balancing forces. This kind of situation comes across in a lot of different problem settings. Um, so basic idea is when acceleration of an object is zero, it has zero acceleration, where it's going at constant velocity, or just standing still, it's a zero acceleration, then a sum total of all the forces will equal zero. But that sum total is a vector sum, and that's where the trouble comes in. Okay, so here is a situation in which we have three forces on a ring. So this is a ring, and you have force 1 and you have a force 2, and this is force 3. And the ring, the important data here is acceleration of the ring is 0. So what means is vector sum of these three forces must equal to 0 from F equals ma. So from F equals ma, one way to think about this is each force is causing its own acceleration. This one is causing acceleration, say a1, and this one is causing its own acceleration, and this one is causing, the third one is causing its own acceleration. And when you add them up, then this side is 0, this side is mass times the net. This stands for a1 plus a2 plus a3, and this side is F, which stands for F1 plus F2 plus F3. So this side is 0. That means F1 plus F2 plus F3 equals 0. And this is vector equation. This is not F1 plus F2 plus F3 is 0. So this doesn't imply that, okay? This is a vector equation, which means direction is important. So one way to think about, one way is thinking components. So this is one way. Another is geometrically, thinking geometrically. We are going to try to use this one because this analytical and kind of very easy to implement, right? You may have already implemented it. So to implement this, it has some well-defined steps. So one of these steps is choose coordinates. So here I have just x and y. So it's kind of natural choice here. So if I go here, this direction we'll just call it x, this direction we'll just call it y, and we'll place O right there at the ring. So second is compute components. Why? So this equation in component form will be f1x plus f2x plus f3x equal to 0, and f1y plus f2y plus f3y equal to 0. So I got two equations inside here. This is one vector equation. So one vector equation is actually here two algebraic equations. So these will have some particular numbers. Okay, so if you put this, this guy from here, we can get for this other guy, what the x components and the y component is. So let's work it out here. I'm going to work out each vector at a time. So this is the f1 vector. It's all along the x-axis, in the positive x-axis. So its component is all just x. There's no y component. So this becomes f1x is 40 Newton. f1y is 0. Similarly, f2 is all along positive, so its component is positive. f2x is 0 and f2y is 30 Newton. So if I plug this in there, clearly f3x is going to be minus 40 Newton and f3y equals going to be minus 30 Newton. So, but I'm not done yet. We have information about the components of f3. What we want is the magnitude and the direction of f3. So let's work that out over here. All right. So we have this x and this y. We have minus 40 Newton in the x direction, so minus 40. Because if you go in that direction, and then minus 30 in this direction, minus 30 Newton in this direction. And so the point, that's the vector, that's where the f is. So, and this angle is over there. So that's where the third vector is pointed. So f equals to square root of 30 square plus 40 square, that's 50 Newton. And this angle here is going to be theta equals arctangent inverse f3y over f3x. And both are negative, so negative will cancel out. And this is arctangent 3 over 4. So that's going to be the answer for angle. And this is the magnitude, and this is the angle. Now the angle, you can see that this angle is some positive amount. Let me pause and calculate the angle. So this is 30. I found that this is 37 degrees. Yeah, 36.9. This is 37 degrees. Now, 37 degrees will be this angle will also be 37 degrees, but this is not the direction it's pointed. So this is not the direction pointed. So how do we say that it's in this direction and not in that direction? Just by looking at the angle. You can't. Just by this angle, just by this value, you can't tell the direction. you need to know which quadrant this is pointed. So from this and this, we know it is in third quadrant. And when you put in their third quadrant, then using this, you say it's going to have to point like that. So beware, many times the student just say this is the angle and this is the magnitude. That's not the complete answer, because this angle doesn't tell you if it's pointed in the first quadrant or the third quadrant. You have to be able to tell that. So sometimes people say, what is the magnitude and direction? So here clearly it says theta, I need to give you this theta. But if the question was what's the magnitude and the direction part, you really have to tell which quadrant is pointed. Otherwise, just giving the angle is not enough. Okay, so let's recap. Whenever you come across a problem that's a balancing forces, a very easy strategy is to choose a coordinate system, and this is your choice. Meaning, I could have chosen something else which will simplify it, okay? Here, it just turns out to be a good choice. As you do more problems, you'll realize which choices work out better than other choices. And then you have to compute the components, and then you get algebraic equations like this, and then you plug into them, and then you solve the problem. You solve these two equations, and that's pretty much it in terms of calculation. And then using those calculations, you can figure out the direction. The direction requires one more step, recognizing which quadrant the force points to, and from there you can tell the direction. Hope this helps. Talk to you later. Bye.